we're going to get practical, very practical in the first session. Tools, workflows, technologies that we actually encounter in the field. And I'm very excited that there is one person that is going to walk us through this session. Ladies and gentlemen, let me welcome to the stage from the survey school, Rami Tamimi. Let's hear it. Rami, my friend.
Thank you, my friend. Thank you. Appreciate you. Good afternoon, everybody. How are you? That was a good lunch, right? Kind of getting ready to sleep, right? So I'm going to try to keep the energy flowing. I'm going to try to encourage you and walk you through the struggles that I face as a PhD student as I build my own custom mobile mapping system. This is a part of my research and what I have been doing over the last several years. And I hope you find some enjoyment and some pleasure in understanding how all of these systems work. Fair warning, these are going to be the most unsexy point clouds that you have seen this entire conference, but I hope that you can enjoy the level of accuracy that we've embedded into them. So let's start with this. Okay, so Elon Musk is not a big fan of LiDAR, right? He doesn't put it in his vehicles. He doesn't think it's a proper sensor that can actually help with self-driving vehicles. You know, he kind of makes fun of Waymo. He makes fun of any company that tries to incorporate these sensors. And I'm sitting in a room full of people that use LiDAR every day. So naturally, I put a LiDAR sensor on my Tesla. This is just the beginning of what would become several months to several years of research trying to figure out if Elon is right or not. This is what people make PhDs on. It's trying to challenge billionaire CEOs. So for those of you who don't know who I am, my name is Rami Tamimi. I am a professional surveyor in the United States. I'm also a PhD candidate at The Ohio State University studying geodetic engineering. I think many of you probably know me from the internet, where we have over 88,000 subscribers and over 7 million views on my YouTube channel. And I am also the founder of the Survey School, a place where you can go to learn about surveying. We'll talk more about that at the end. But I'm just really excited to show you what I've been working on, honestly. So the first approach that I wanted to take with this is understanding what sensors I needed to add to my Tesla. And I was like, OK, I have a GNSS receiver, right? This is an Emlid Reach RS3. I'm just going to attach this to the top of my vehicle. And theoretically, I should be able to just drive normally and capture positional data. So I just ran an auto capture every second. And as I drove my car around, this is a library in my area, I was able to capture, fairly accurate GNSS positioning. And using the heading of the GNSS, I can figure out my kappa value and estimate the trajectory of the vehicle. So pretty basic test, went well. Not to let me. Come on. Oh, I guess we have to finish the loop. All right. Finish the loop. Can we go to the next slide, please? Thank you. So then this became a much bigger project, right? This is my advisor, Dr. Charles Toth at Ohio State. We put together this giant rig, this custom mobile mapping platform. And using this platform now, I will be driving around campus, collecting as much data as I can using my Tesla. So what's the sensor stack, right? At the front and at the back, we have two Velodyne VLP-16 LiDAR sensors, right? Very standard VLP, easily able to extract frames of each, LiDAR frames, I guess, as you're mapping, and be able to integrate them into your workflow. And then I put a Novatel SPAN IMU sensor so that we can get our omega phi kappa values. And then on top of that, we had two GNSS receivers, one Emlid Reach RS4 Pro, second RS3, and actually had two additional ones, so I had four. You can see the other two over there. We didn't use them. I used the Emlid receivers for this experiment. On top of that, we had a very special sensor on there. This is Share's S20 scanner. This uses both GNSS IMU integration as well as SLAM. And it's really important to understand the SLAM side of things, because you're going to see kind of where this project kind of took a turn. But anyways, that's just there for fun. And then a whole bunch of cameras, right? The idea is that we will eventually do the thing that you guys all love doing, which is Gaussian splatting. I don't want to do that just yet. I want to make sure I actually have an accurate point cloud before I get into that. But the cameras are all there collecting data so that when we get to that stage of our research, we can go ahead and use them. So here's a diagram showing the entire sensor stack placed on my vehicle. Next, what we're going to do is take the GNSS data and the IMU data and go ahead and correct it. So you can see it's very, very noisy, especially around this loop. You see that white dots, how noisy it gets? It's because these are all single position GNSS observations. We need to use a base station to correct them so that we can get that centimeter level accuracy for our trajectories. So running this through Inertial Explorer with a tightly coupled process, I can go ahead and figure out what my exact centimeter level accuracy is, as well as our rotation with our IMU. So in a minute here, you'll see everything turn green, or hopefully green. Green means that it was good. Processing almost complete. It applies a smoothing factor, so some filtering as well to ensure that everything comes out clean. There we go. So now we have nice, clean GNSS and IMU data that we can incorporate into our mobile mapping data. Next, we'll go into VeloView, and we can actually see all of the frames. This is sped up, I believe, at 20x? Yeah, 20x speed. So you can see all of the buildings on campus. You can see in the center, there's no laser. You see right here, this area, this is the stack, right? This is our rack with all of the different sensors. We'll obviously filter that out, but you can see as it's moving around, that's where our vehicle is. And we're just collecting as much data as we can along campus. So after processing the GNSS data and the IMU data, we get this, right? This is our GNSS and IMU point cloud. Now what you noticed is this is fairly noisy, right? It's not exactly the clean, crisp point clouds that you expect, but it works, right? It gives me the accurate data that I need. And this is the point cloud that I'm going to have to work with and try to refine the sensor settings in order to improve it. Now, those of you that work in this space and understand how the data integration happens might be screaming at me, why don't you just use SLAM? Simultaneous localization and mapping, it's great. It's perfect, right? What do you need all these sensors for? This is why. So if we use an ICP and just do frame-to-frame referencing, sure, I get a nice, clean, crisp point cloud that just floats around in space. It's not georeferenced at all. And it bends and it curves and it does all sorts of crazy things, right? And sure, I can bring in some control and try to clean this up, but at the end of the day, this data is barely usable, right? So you need the sensors. You need to georeference your data. You need to know where it's at. Running just an ICP like this is not going to be enough. So let's take a look at the noise, right? So this point cloud, okay, although it's warped and it's all over the place, right? We could still see individual frames and see how well the LiDAR sensor performed. And this is actually pretty decent, right? This came out at about 5 centimeters. So 5 centimeters of noise, we are moving, we're not staying stationary. This is not a static terrestrial scan. So we can expect that that's probably what's gonna happen. When we looked at this point cloud with the georeferenced GNSS and IMU data, we were closer to like 20 centimeters. So significantly more, but that's because we have, well, a lot more error to deal with. Okay, so that's our custom system. That's what I need to work on, and that's the data that we're trying to improve, and the whole system needs to be improved. Let's say we have another system that we can compare it to. This is called ground truthing. So I have this handheld SLAM scanner that has GNSS and IMU sensors on them. We should be able to validate the accuracy using this. Well, this is what happened when I processed the data. And this is something, I talked about this yesterday with, working with companies and trying to better understand the true capabilities of these companies. This is what the results were. And this is a clear indication that there was no GNSS and IMU data being incorporated into the data. This is purely SLAM, and we get the staircase effect, right? So I worked with the company and said, hey, this is the results I got. What can you do to help me? And we worked together, and we were able to eventually get a data set that looks like this. The only problem with this data set is it's not georeferenced. So local coordinates, relatively probably accurate. But I mean, looking at it, it looks fine. It looks good. They didn't even mess with the camera to LiDAR calibration. We just kept the LiDAR point cloud. So here I am, I'm taking a section here to take a look at the building, and yeah, I mean, the building looks pretty decent. One thing, and I don't know if I put the video in, I don't think I included the video in this presentation. So this point cloud is fine, right? The building looks okay. I think we had probably 3 to 4 centimeters. But then when I went to a different part of the building, or a different part of the scan, I would look at buildings that had double faces, right? So with double faces, then you have a calibration issue. So it's kind of hard to say that this is a point cloud that I want to use for research. The reality is this is not ground truth data. This is just another experimental data set from a system that's really not designed to do this. It's a handheld system. Okay, so what do I need to do? Where's Michael? You remember that discussion we had on that live call? What did you tell me about if someone's having all kinds of issues with SLAM point clouds? What should they do? No? What do you recommend they buy? An entry-level TLS. So I went and I got one, right? I followed Michael's advice. See, I listen to other people too, right? And I went back to campus, and this was last week, actually. This is literally brand new data. And I went ahead and generated 70 control points. So you can see I used the Emlid Reach RX2, and I just measured the points and then replaced them with a target. And I put them all together, and I said, okay, I've got this data set that has 70 control points. I should be able to reference everything to the data. And so went and scanned. I think we had like 40 stations or setups. And now, finally, for the first time ever, I actually have real clean TLS data that I can work with. And this is the reality of it, right? Like sometimes you have to do the hard labor, the in the field, the boots on the ground work in order to get proper ground truth data. And that is the only way that you can assess the accuracy of your experimental data, right? Or new sensor data, whatever it is that you're doing. Until you go out there and actually are putting control in the ground and actually using proven equipment. I'm a big total station guy because I'm a surveyor, but a TLS is going to be the more appropriate approach here for this project. So everything comes out nice and clean and crisp, and camera to LiDAR calibration is there too, so I can do some experimentation with the cameras. Love it. And then we went and took a profile just to see if there's any noise. I mean, there shouldn't be, but just to stay consistent with the other point clouds. And we take a look here, and I believe this was at 3 centimeters. So very, very clean. The point size is just huge here. I think I drop it at some point. Yeah, there we go. I start dropping it. So yeah, 3 centimeters between, for the noise on the building side. Perfect. Looks good. So here are the results, right? This is the absolute accuracy between my georeferenced GNSS IMU data. So not the clean staircase-looking ICP data set. This is the georeference with noise data set. And you can see in open skies, we were getting about 9 centimeters. Under trees, we're at 11 centimeters. And then Neil Avenue is actually a part where the GNSS fails a lot. Just in general, there's a bridge there. There's a lot of trees. It's heavily corridored. So that is the one point on campus that really struggles. We got 18.5 centimeters there. Comparing the relative accuracy of our GNSS data to the TLS, shorter baselines, under 50 meters, 7 centimeters. Once we get to 150, 7.5 centimeters. And then 2 long stretches I did on the long ends. They were about 300 meters. We got 8 centimeters of error. So my mobile mapping system, although very noisy, is getting about 8 centimeters of relative accuracy. So that tells me that the registration is coming in decent, not great, but decent. So that's not my research project, right? This is all just to establish ground truth data for what I really want to do. And what I really want to do is see if anybody can do this using just cameras. And the cameras I'm referring to are the dash cam footage that you get out of the Tesla. You see, I have this theory, I have this idea that I can take these cameras and run an internal calibration to get my focal point, my pixel size, all of the different camera parameters, undistort the cameras. So this is the back camera, you know, when you back up your car. Undistort the image, right? And then take that a step further, localize my camera's orientation. So figuring out, okay, I have some control points, I survey them, I georeference them in my camera frames, figure out what the, RMS error is there, and get my omega and phi value. And then with that information, be able to add IMU data and GNSS data, and then extract frames that come out of my videos. So I'm going to set this to, 2 frames per second. I'm going to go for my omega phi kappa, or yaw pitch roll, doesn't matter. It's just different setup. And there we go. Now while I'm driving, I don't have to have any sensors, except maybe a GPS on the top of my car. And I'm driving, and I'm generating all of these frames from just the video footage that is coming out of my Tesla. Here I am, I'm just driving, minding my business. Anybody can do this. This isn't very difficult. It would be great if I could access the GNSS that's inside of the Tesla, but I can't. Maybe I need to be nicer to Elon so he can give me that access. At any rate, I can even click on one of these images. I think I do at some point here. Come on, Rami. You can do this. There we go. And I can view this image. And this image is going to be tagged with a GPS position and an orientation of omega phi kappa. So I love what I do. I love teaching. I love this industry. And part of this, allowed me to go into YouTube and make content and make this stuff really interesting and entertaining. And by doing that, we actually established an online school called the Survey School, where anybody can learn about surveying, no matter where you are in the world. We do meet up in person. We do things, like workshops and attend conferences together. But really, we built this online community so that anybody can get into this field, better understand how surveying works, and incorporate geospatial technology in their workflows. So if you're interested and you want to learn more or hear about many of the people that have joined, their stories, and the things that they've done and achieved, you can scan this QR code or visit thesurveyschool.com. And that's it. I appreciate all of you, and thank you for having me.
Let's give it up for Rami.
Thank you, buddy.
You've got a fan club over here.
Wow.
Awesome. Let's take a look at the questions that came from the audience. So,
all right.
did you call the RTC360 an entry-level laser scanner?
That was Mikel's words, not mine. I was just going off his advice.
Okay, so we can skip on that one.
Yeah,
okay, next one. What do you think is your largest advantage against the rivals with the scanner?
I would say the only advantage really that I have is that I incorporate survey control, right? A lot of folks, they don't see the value. They just want to scan, attach a bunch of registrations together or a bunch of setups together. They create a bundle and they're like, oh, okay, this is probably good. And the reality is you need to be able to verify your data. So if you're not establishing survey control, if you're not using different sensors to collect data, how do you know your data is actually valid? How do you know that you're delivering good quality work? That's the advantage I think me and many surveyors that are in this field have. And we encourage everybody to be able to do that because it's not that it's hard. It's just an additional layer of work that you have to add onto your workflow.
Awesome. Next one from Jeffrey. With good INS and PPK, do you ever need dual antenna for mobile mapping?
So you can do multiple GNSS receivers, and actually this can supplement the INS data set. You don't ever need it. You just need one rover with your IMU and then a base station. So I guess, yeah, base station is separate from the antenna on the vehicle. You can have multiple rovers, and this will kind of give you the lever arm as you kind of turn, and you have different radiuses when you turn. The lever arm will basically be more accurate. You can calculate it better. So it's just an additional layer of help. That's all.
Got it. Rami, does your Tesla still work after all this?
Yes. My wife was fearful of it, but no, it's all good.
Awesome. And let's wrap it up with this one on a practical note. Do you have some videos of your work on YouTube?
I have everything on YouTube. It's literally a library of my entire history. So check it out, youtube.com/Rami Tamimi.
Okay, perfect. Okay, ladies and gentlemen, let's give it up for Rami Tamimi. Thank you so much.
Appreciate you.